last time we started discussing the nonlinear characteristics of the optical fiber. And so specifically we had discussed stimulated Brillouin scattering. So we saw that how initially for low data rates for the first generation of optical links, it was a problem, right? But for the current day, the high data rates we operate at in many gigabits per second, basically the bandwidth of the signal is now large enough that the Brillouin gain spectrum is very narrow compared to that, and so basically it's not a problem anymore for optical communication links. So I just also want to just mention that SBS is also used in sort of signal processing. So it can also be, so we sort of looked at it as a problem in terms of communication, but recently it's also being used as a tool for optical signal processing, or specifically so this field of microwave photonics. Okay, so it's basically processing RF or microwave signals using photonics, right? So basically what we do is whatever the RF or microwave signal that you want to process, right? So you use an electro-optic modulator and then you put it onto your optical carrier, right? And then you do sort of SBS in some fiber, and we saw that. So, for example, SBS gives some gain response like that, right? According, so along with this, there's also some phase response, right? So this is like the gain or amplitude response, and then there's a phase response also, right? So there's a frequency-dependent phase. So basically, so you have some signal here, so you put it onto a laser, and typically from the other direction you send in a pump, right, to sort of have the Brillouin gain onto your signal, right? So this frequency is the signal frequency µs, and this pump is µp, right? So the difference here is the Brillouin frequency, right? And so then if you have some signal on here, right? So around µs, if you have some signal, RF signal, right? So you modulate your optical signal at µs. So you have the RF signal that you want to process now centered at µs. And then now you can modify this spectrum, or basically the signal you want, you can process it in various ways depending on, so basically this, you can see there's a frequency dependent gain and also a frequency dependent phase across my signal, right? So basically you can think of this as applying some filter, right? Like some h of f that I'm applying on my signal, right? And then by tailoring the pump, for example, you could have multiple pumps, right? So you could have like multiple gains all interfering with each other. You could play all sorts of games here. So this is a whole field of microwave photonics, where basically you can make, so for example, you can make filters, delay lines, different kinds of signal processing elements for RF or microwave signals, which can sort of surpass the traditional electronic equipment that you use, right? So you can go to higher frequencies, do better in terms of noise, etc. Right. So that's a active field of research also, and it's sort of developed over the last 10-15 years. This field of microwave photonics. And then one more comment, just so at the end of the last class, one of you had made this comment that basically you can reduce the nonlinear effects, so SBS or any nonlinear effect in general, So because the nonlinear strength of the fiber scales with this factor L effective by A effective, right? So the effective length for nonlinear interactions is inversely proportional to the loss, right? For example, if you want to reduce this number, then we can reduce L effective, but that would mean increasing the loss, right? So that's of course not useful, right? If we are just increasing the linear loss, so that would attenuate our signal even more in the fiber. So you can't do anything about this. So then what one can do is increase A effective, right? So that's the mode area, right, of this mode in the fiber, right? So one simple way is you can think of, if you increase this core size A, then basically sort of the mode area will also increase. Okay, so such fibers are known as leaf or large effective area fibers. Okay, so people have developed fibers with larger core sizes, which gives an effective larger area, right? So this leads to reduction in nonlinear strength. So yeah, in certain places they are used, but again, you don't get this for free, right? Because now again, so if you increase this core size, you can imagine that. So if you still want to maintain the single mode condition, right? You want this V number which is proportional to, remember, the core size, right? So if you increase this beyond a certain point, then now V becomes more than 2.4, right? And so now it will go into multimode fiber, which we don't want, right, for considerations of dispersion, etc. So then, for example, you have tried to compensate that with the index difference. So this was also proportional to the index difference here, right? So you try to reduce, if you increase A, you have to reduce delta further if you want to still be in the single mode regime, right? But delta was already very small, right? So for standard single mode fiber, this is already like 10 to the minus 3 in that range. So making this even smaller is not easy. So you have to, of course, take into account these other considerations, and also for a larger core, the bending losses, etc., also increase. So, so this is a solution used in some particular applications. You can't use this everywhere, especially for very long telecom links, right? Also, there are already conventional single mode fibers laid down, and we want to use them. It's not cost effective to replace all these long links with new fibers. But yeah, so. Okay, so the next nonlinear effect that we'll discuss is stimulated Raman scattering. So this is also a type of nonlinear light scattering that happens in the fiber that we briefly discussed last time. Just the scales are quite different from Raman scattering. Right, so I mean, many of you might know of the Raman effect already, right? So if you send a laser with some frequency omega p here into a medium, then basically the light can couple to the vibrations of the molecules or atoms that make up the medium, right? So these are typically high frequency vibrations, typically in the terahertz range. Okay, so so they're basically what are known as optical phonons, right? And basically they can absorb a certain part of the photon energy and then scatter a new photon which is at slightly lower frequency. Okay, and this is basically the Raman shift. Okay, so basically there is some vibrational state here, which is so you have some ground state of the atom or molecule, and then there's some vibrational state which is slightly higher energy given by the vibration frequency. Right, so again, just like SBS, your incident wave is known as pump, and then the scattered wave of lower frequency is known as Stokes. Right.
So can you make it a little bigger?
The Raman shift.
So can you
Is there a
write a
question?
little bigger? So can you write a little bigger? This
Uh,
the
okay.
words. The camera quality is not good, so I can't see that whatever you're writing.
Okay, I try to write bigger. So I mean, probably the quality is different for different people depending on uh, your internet connection at your place. But I'll try to make it bigger. If you go probably look at the recording, it's probably better quality than the live stream. But yeah, so this is the pump omega p. This is the scattered photon omega s. Right? Obviously, omega is less than omega p by an amount omega r sub r, which is 2 pi f r. Is the Raman shift. Okay, so these are localized vibrations. So we saw that for Brillouin scattering, basically uh, it was sort of a non-localized. It was like a propagating sound wave, right? But here, basically, so like if you look within the fiber, like this thing is happening locally at. So you have these SiO bonds, right, which are vibrating, and so they are sort of vibrating locally. Okay, and each of them are sort of scattering these independently. Okay, so it's not like a coupling to a delocalized sound wave like in Brillouin scattering, um, but sort of local vibrations. Okay, and so now, so there is no grating or anything in here like the Brillouin scattering, right? So basically now you can have both forward and backward scattering. So if your pump is propagating in the forward direction, then you can have a Stokes which is either forward or backward direction. So unlike the Brillouin scattering, which was basically, so because this grating is set up, there is a back reflection. But here, like you could have forward or backward. And actually, mostly in optical fiber communication, we worry about forward scattering because, as we'll see, sort of the main distortion that Raman scattering causes is for sort of when we do WDM and send multiple wavelength channels in the same fiber. So you can imagine, for example, if this is one wavelength channel and this is another wavelength channel, then these two can couple and you can transfer power from one to the other. So right, you distort the signal. There will be some crosstalk and the signal in each of the wavelengths will be distorted. Right, and so of course these signals are all propagating in the same direction from the transmitter to the signal. So typically forward scattering is what we worry about in optical fibers, but just so you know, you can also have backward Raman scattering. Another point is that forward scattering is more efficient, right? Because remember, again, you have these pulses which are traveling, right? So the co-propagating pulses, of course, interact more, right? So if you have a pulse at omega p and another pulse at omega s, they of course interact more traveling in the same direction. Whereas if they're traveling in the opposite direction, you can see that they'll just interact for a very short time and then quickly pass over each other. Right, so the backward interaction will not be that efficient just because of the finite interaction time. Whereas here, like co-propagating will interact over sort of the entire length of the fiber. Okay, so basically it's a scattering effect, just like Brillouin scattering. Just the these frequencies are different, and it can occur in the forward direction. So again, there is a Raman spectrum just like a Brillouin spectrum. So if you have a pump frequency, then it scatters to the Stokes frequency, and then there is some spectrum here. Okay. Just like we had this Brillouin gain spectrum, there's a Raman gain spectrum. Okay, so this shift is FR. Okay, so if we look at this in sort of accurately, I guess. So in glass, this sort of looks something like this. Okay, so we saw for the Brillouin, this is like a very narrow Lorentzian, right? But for Raman, it looks sort of this weird shape, starting almost at the pump frequency and then slowly increasing up to this peak Raman shift and then going down. Okay, so for glass, this shift here is about so this peak occurs here at about sort of 13 to 15 terahertz, in that range. Okay, so again, compare this to the Brillouin scattering where the shift was like 10 gigahertz. Here we are talking about 15 terahertz, right? So that's 3 orders of magnitude higher. So the shift is much larger, right? That's basically because these vibrations are at much higher frequency, like these optical phonons, as opposed to the acoustic phonons. Okay, so this is some complicated shape here, which depends on basically these SiO bonds. So first of all, again, glass is the amorphous material, right? So you can imagine that there are various different modes of these vibrations, and so instead of a narrow line, so if you had crystalline materials, right? For example, if you take silicon, then the Raman spectrum is again a nice narrow line at a particular shift with a very small bandwidth. But once you go to amorphous materials, basically this gain spectrum broadens out quite a bit, right? And this is basically some sort of inhomogeneous broadening. Basically, now you have not a particular crystalline structure, but again, you could have different SiO bonds with some dangling bonds lying around. So you can imagine that there are sort of many different narrow gain spectra, which are all sort of shifted from each other depending on the local environment around each place. And then when you add all of them up, you get this sort of broad spectrum. Okay. So this peak occurs at around let's say 13 to 15 terahertz, and it goes up to almost like 20 terahertz here. This is okay, and if you look at the y-axis, so if we have got here the Raman gain coefficient, again in meter per watt, right? Just like the Brillouin gain coefficient we had in meter per watt. So the units are now 10 to the minus 14 meter per watt. For Brillouin, recall this was 10 to the minus 11. Okay, so here you can see the values are much lower, again because of this broadening, right? So basically what has happened is instead of all of them lining up to give you a very narrow and high peak, they've sort of all spread out and dispersed so that the peak is much lower, but spread out over much larger range of frequency. Okay, and so here it almost goes up to like 6 times 10 to the minus 14. Okay, so now this is not a simple Lorentzian shape anymore. So just for ease of calculation and sort of designing our links, what is done is to just make a linear approximation here. Okay, so this gain spectrum is just approximated like a linear function here. Okay, up to about like 16 terahertz. So we just approximate this function like a triangular profile, like a linear gain spectrum with frequency until about 16 terahertz and then 0 afterwards. So it's an approximation to the actual gain spectrum, which is more complicated, but it helps in ease of calculation, and it's close enough that you can sort of design your systems using this simple formula. So in this linear approximation, the Raman gain spectrum, basically you can write as this is f, the frequency shift in terahertz divided by, right, so we go up to 16. So for example, and this is a peak Raman gain, which you can see happens at f equal to 16. Right? So this is, we use only for up to 16 terahertz, and then we say 0 for right. So the peak gain occurs at f equal to 16 terahertz, and this value is about 7 times 10 to the minus 14 meter per watt. Okay, and basically again, what this Raman scattering does is it couples waves traveling at so if you have two waves in the traveling in the fiber, one at the pump and the other at Stokes, which lies within this gain spectrum, then they couple, right? Just like the Raman scattering, we have now propagation equations for the pump and Stokes. So for the pump, this Raman scattering will act like a loss. Right? So again, this I, P or S is the power at the pump or Stokes divided by the effective mode area. So it's the intensity. Okay, so now again, this is a nonlinear coupling. So product of the intensities with the Raman gain here, minus sign for the pump. Right, so now, as we said, we consider the pump and Stokes co-propagating usually. So, and both are traveling in the plus z direction. Right, and then we could again have the usual linear loss. And then for Stokes, it's also traveling the plus z direction here. Right, recall again for below we had a minus sign here because it was traveling backward. And so now for the Stokes, it's a gain, so this is U plus. And you could again include linear loss. Right, so again you can try to solve these propagation equations starting from z equal to 0 for some particular input pump power and some Stokes power, and then see how they evolve. Right, so basically what happens is that you can see that you scatter power from the higher frequency to the lower frequency, right? So the Stokes will grow and the pump will decay. Okay, so if I look at the pump, it will decay. Right? So even if you neglect the linear loss due to this Raman coupling, the pump will decay, and with the linear loss, it will decay even faster. Right? So it starts from some input pump power here. So this is the pump power as a function of distance, and then the Stokes power. Let's say it starts from some very small value. Then it will start growing due to the gain experienced by this Raman scattering, right? And so again, we can sort of calculate like for what input power here. Again, this Stokes, because you can see that the gain here is proportional to the pump intensity. As I increase my pump power, this Stokes will actually grow faster, right? So again, we can estimate sort of just like the Brillouin scattering, we estimated some threshold, right? So again, there will be if you look at, for example, at some output here, if you look at the Stokes power versus input pump power, right? So like up to some threshold, it will sort of let's say vary sort of linearly, and then suddenly it will shoot up exponentially beyond a certain threshold. Okay, so you get some nonlinear behavior like that. So we can estimate again at what point this happens. By sort of numerically solving these. So that threshold for the Raman is again the sort of same expression that we had for Brillouin. Okay, so we get the same expression A effective by L effective, and then the Raman gain coefficient. We had the Brillouin gain coefficient for the Brillouin case, and there we had 21. Here we have 16. Okay, so this is estimated. So basically, at this power, sort of the Stokes power becomes 50% of the input pump power. So basically, we've transferred 50% of the power now to the Stokes at this threshold. Okay. So basically, again, the rule of thumb is basically if you want to avoid Raman scattering, then you have to be below this threshold power. Okay. Again, so if we put in the numbers here for a standard single mode fiber, for example. So recall again, when we did this for Brillouin, we got a number which was like 5 milliwatts, right? So there, the gain coefficient was about 10 to the minus 11 or something, right? Here we are sort of a couple of orders of magnitude lower, so this number is higher by a couple of orders. So this comes out to be about 570 milliwatts. Okay, so this is for, again, if you take A effective, let's say 50 micron square, right, L effective to be 20 kilometer, which is like 1 over alpha for 0.2 dB per kilometer. Okay, and this GR to be again that's 7 times 10 to the minus 14. Right, so you can see this is now a very large amount of power here, 500 milliwatts, and typically, as we discussed last time, also the powers that we use for optical communication are typically in the tens of milliwatt. Okay, so typically we are much below this threshold for Raman scattering, where we transfer like half the power to the Stokes. Okay. But that doesn't, so basically what this is saying is like, let's say if I have only one channel propagating through my fiber, then the loss that I get due to Raman scattering is negligible if my powers are in the tens of milliwatt. Right? So if this is 500 milliwatt, usually I'm operating here. So basically the loss to the Stokes is very negligible, right? So unlike, for example, in the Brillouin case, where we had like the Brillouin sort of acted on each channel individually, right? And there was no coupling between different wavelength channels. Here we can see that for individual channels, the Raman scattering doesn't do much. But if you have multiple wavelength channels, right? So let's say if you have some WDM now with multiple wavelength channels, all propagating through the fiber here, so you can see all of them. Let's say they lie within this gain spectrum. So typically, again, let's say if you look at the typical DWDM grid used today, so this wavelength or the frequency spacing between adjacent channels 100 gigahertz, right, or 0.1 terahertz, right? So you can see that. So whereas this Raman gain spectrum you're talking about is sort of 15 terahertz, right? So you can see a lot of wavelength channels will fit in within this, right? And all of them will now transfer power to each other. Like maybe small, but because you have so many channels now coupled to each other, right? That will lead to distortion in the data. Okay, so right. So let's say I have multiple wavelengths. Right, traveling through my fiber. So then, because of this Raman scattering in the fiber, you can see that the power gets transferred from higher frequency to lower frequency, or in wavelength, basically from lower wavelength to higher wavelength. Right? So basically, and so all of these lie within the Raman gain. Right? So basically, you can see what happens is that so from lambda 1, I'll transfer power to lambda 2, lambda 3, lambda 4, all the high wavelengths. Similarly, from lambda 2, I'll transfer power to lambda 3, lambda 4, etc. Right? So basically, at each wavelength, I'll transfer power from that wavelength to the higher wavelengths, and I'll receive power from the lower wavelength signals. Right? So you can see that if all of these have some data on them, which is different, right? Then if this gets transferred onto here, right, there will be some, of course, distortion. So this is known as crosstalk. The data of different channels getting mixed up with each other. Okay, so again, if you look at this propagation equation, so if I look at the first channel, for example, the power in the first channel, right? So basically, that will be so if I look at what is the power transferred from lambda 1 to some lambda mth channel here, right? So that will be proportional to the gain coefficient, which depends on the difference between again lambda 1 and lambda n, right? So depending on where that mth wavelength is, how far it's separated from lambda 1, that will give me what value of this Raman gain coefficient is. So right, that will be this E1 comma n. And then it will depend on the powers in the in channel 1 and the mth channel. Right, so basically I'm just rewriting this equation. So we had dIP by dz equal to minus, so Raman gain IP IS, right? So now pump is my first channel and Stokes is my mth channel, and so I've just written I as P over A effective, so I get an AF. Okay, so let's so just consider the nonlinear term here, not worry about the loss here. We can sort of estimate if our powers are much lower than this threshold power, right? So we are still sort of in the sort of the linear regime of scattering. Okay, so we can basically just linearize this. So we can say that the change in the power in channel 1 is just this coefficient multiplied by the propagation distance here, which, as we know, for the for nonlinear effect is basically L effective, right? So that's the effective length over which the interaction is happening, right? So basically, we are just linearly integrating this, assuming this does not change much, right? So this is for delta P1 much smaller than P1, right? So basically, the loss, the fractional loss in power is small again. So if we are much below threshold, so we said at the threshold, roughly let's say 50% of your power is transferred to the stocks. We are much below that, so we are, let's say, a few percent power transfer. In that case, we can sort of roughly estimate the loss in power like that, right? So again, it's proportional to L effective by A effective here. Okay, so now let's say if we have, if of course we have now multiple channels, right? So this M goes from, for one, for example, it goes from 2 all the way up to capital N, where N is the number of wavelength channels, right? So if you look at one more thing is that, so this G, the gain factor coupling the first channel to the mth channel, right? That will be basically this G, the Raman gain function, at the frequency which is M times the channel spacing, delta F channel, right? So again, so if let me draw that again here. So if I look at, so if this is lambda 1 and this is lambda m, right? And we are saying that the frequency spacing between the consecutive channels is delta F channel, right? So again, for the DWDM case, this is 100 gigahertz. So then the frequency separation between the mth channel and the first channel will be m times the channel spacing between consecutive channels, right? So basically, the gain, effective gain that will come here will be the Raman gain computed at a frequency separation of m times, right? And so remember, we basically linearize this, so we can just write this as this GR times m times delta F channel divided by this 16 terahertz. Right, so we can see that basically this gain coefficient scales linearly with the channel number. So the higher the separation, the more the gain, right? So basically this will transfer more power here and then lesser power to the closer channels, just because the gain coefficient goes up with higher separation. Okay, so this is basically the loss in power of channel 1 due to coupling with the mth channel. So if you want to calculate the total loss for channel 1, basically then we have to add up all these effects for all m, right, from 2, 3, 4. So if we have let's say we have n total wavelength channels. Right, so then this so-called fan-out factor, right? So F is defined as basically, so this is delta P1 over P1. So the fractional loss in the power for channel 1, Okay, so the fractional loss in power is basically delta P over P1. If I bring P1 to this side, then you can see that just G times power in the MH channel. So again, typically for these WDM systems, at the input, all the wavelengths have the same power. Okay? So let's say that the input power in all of these are the same. This is typically the case. Okay, so then this finite factor here you can see I can write as, so I'll have to sum this m starting from 2 to the number of channels. Right, so that will be the peak Raman gain here times this m delta f channel. Okay, I'll write that below. Right, so this I can write as this will be 16 terahertz. Now multiplied by PM, which is just P in. L effective by A effective here. Right, so basically you can see like all these numbers are sort of constant, and you just have a m here. So you have a summation of the natural numbers from 2 to n. Okay, so that's, I mean, it's a standard formula for that. So this you just get n times n minus 1 by 2. Then the peak Raman gain. Then the ratio of the channel spacing to this Raman shift frequency. Then input power, and then this factor of L effective by A. Okay, so that's the fan out factor for channel 1. Right. So the channel 1 will be the worst affected because it loses power to all the wavelength channels. Okay, so typically as a figure of merit, we want this fan out factor to be less than 10%. Okay, so the fractional loss in power should be less than 10% over the link due to this Raman scattering. Okay, so then basically if you plug in the numbers here, so n is the number of channels, right? So basically we get some condition on, so n times P in is the total power input, right? P in is the power per channel and n is the number of channels. So this is the total input power here. And then here we have n minus 1 times delta f channel. Okay, so basically n I've clubbed it with Pn, n minus 1 clubbed it with delta f channel. So n minus 1 delta f channel is basically the total bandwidth occupied, right? So from lambda 1 to lambda n, right? This is delta f channel, then this whole bandwidth here is n minus 1 delta f channel, right? So again, if you have a DWDM link, let's say 0.1 terahertz spacing between each channel, and then you have plus 100 channels. That's too large. So let's say if you have 20 channels, then 20 times 0.1 terahertz, that will give me 2 terahertz as the total. Right. okay, times L effective here. And then these are constant, right? So GR we know is 7 times 10 to the minus 14. The 60 terahertz is a constant number. 2 again. So all those constants we club together and we get a number. So to satisfy this condition of the fan out being less than 10%, basically this number has to be less than 3000 milliwatt terahertz kilometer. Okay. So this you can first part here is power, right? N times P in. So that gives me the what milliwatts here. This is the channel. This is the total bandwidth occupied by the WDM signal. So that gives me the bandwidth here, terahertz, and then length. Right. Again, so for long links, L effective is we can just replace by 1 over alpha. So that will be 20 kilometers here. So then that this kilometer will I just divide by 20 and the kilometer goes away. Right. So I can equivalently write the condition as the total power. So the power per channel times the number of channels times the total bandwidth that I'm using has to be less than 150 milliwatt terahertz. Right? So you can see, for example, if I use a WDM system with, let's say, so again, you can see, so let's say a frequency spacing of 0.1 terahertz, right? So then from this, we get that the total power has to be less than 1500 milliwatts.
Yeah.
Well, sorry. Let's say if I'm using, let's say, 20 channels with 0.1 terahertz spacing, then I have 2 terahertz here. So then the total power is restricted to 75 milliwatt, right? And now, so 75 milliwatt for 20 channels. That means per channel I have roughly, let's say, 3.75 milliwatts, right? So you can see that basically it puts a restriction on the power per channel I can send, given the number of channels I want to use, right? So due to this nonlinear coupling, basically, without this, you might think that, all these channels are independent, right? I could just increase my data rate forever by putting more and more channels. But here you see that as I increase the number of channels, the power per channel has to go down, right? So that will again limit my link length because given the attenuation, right, for a particular SNR at the receiver, if my input power is restricted, then that restricts my link length.
Sir, in G1M, why we have not written M-1 delta FCH? G1M, sir.
G1M what? Yeah, so what?
Sir,
So G1M,
M-1 into delta FCH. Like here we have N-1.
yeah, I guess. This is M-1. Yeah, so then the sum would be like M-1 or the sum of M from 1 to N minus 1. Yeah. Okay, so you can see sort of this graphically more clearly. So right, so this condition I can plot. So the total power times the total bandwidth has to be less than a particular number. So recall that for very long links, right? So if you have amplifiers in between, so once we go beyond hundreds of kilometers, then we typically use amplifiers, right? So let's say every 50 to 100 kilometers somewhere here. So this L effective for long links, recall, is basically the number of sections here, right? The number of amplifiers divided by the distance between each amplifier, right? Or sorry, if this LA, so typically if it's greater than 50 kilometer, then we know that the L effective for each section is basically just 1 over alpha or 20 kilometer, right? So the total effective length, because the power is increased back after the amplifier, is we add each section, so we get NA times 1 over alpha, right? Or the number of sections I can also write as the total length, right? So if I have a total fiber length, link length of L, then N is basically the link length divided by the number of sections here, or length of each section. So I can also write this as L over LA times alpha, right? Where L is the total link length. Right. So this particular thing is only for link with no amplifier. Right. So this thing here, we just put L effective as 1 over alpha or 20 kilometers. So this is for just a simple link, like you have a transmitter, then fiber of length L, and then receiver. Right. Now, if you go to long sort of transcontinental or terrestrial links, then basically you have now amplifiers in between, right? So now L effective I can write as the total link length divided by some constant number, right? So now alpha is a constant number, I know, 0.2 kilometer. LA is also now a number given by what is the how often I have an amplifier, right? So if you use this, then you can see that I'll get some condition on the total power times the total bandwidth, right? Times the total length. Right? If I write L effective like this. So with amplifiers, right, there is a condition on the total power that I use, the total bandwidth that I use, times the total length has to be less than some number. Okay, so you can see that if I want to use more channels, either I have to reduce my power or reduce my link length, or equivalently. If you want to increase my link length, I have to reduce the power in each channel, the total power, or reduce the number of. So that's a trade-off, right? You can see that the total data rate that I achieve also depends on this F total, right? Because that just gives me how much. So the total data rate that I am getting is sort of roughly F delta F total, right? That's right, because basically I put data on each channel, and the channel separation is equal to sort of the data rate so that the neighboring channels don't interfere. So you can see that the total data rate effectively that I'll get will be this. So again, there's a restriction on the data rate times length, like we had, for example, for dispersion, right? But now there's also power coming here because of the nonlinear, because it's a nonlinear effect. Okay, so I can graphically see this like. So again, if I want to increase the link length, then I have to reduce the power, transmitted power, right? Which is sort of opposite to what I actually want, right? Typically, like as I'm increasing the link length, I want to send more power at the transmitter, right? Because I want to compensate for the extra losses and noise occurring over the longer length. But due to this nonlinear effect, we can see that actually, if we want to avoid this Raman scattering induced crosstalk, we actually have to reduce the power, right? So somehow we'll have to compensate for this drop in SNR in some other manner, right? So you can see how the nonlinearity is directly affecting my system performance. Yes, there's somebody has raised hand. There's a question. Should you have a
how across the frequency spectrum, how these channels are separated?
How means like we just talked about that, right? So typically, I mean, you could have different systems, but so the modern dense wavelength division multiplexing network that is used, typically the separation between each channel is 100 gigahertz. So that's delta F channel. And so you can put data of roughly like 50 gigahertz bandwidth on each channel. Right, so this can be like 50 gigahertz. So in each channel you have roughly, let's say, 50 gigahertz, or so typically you put like 50 gigabits per second per channel.
Sir, what is the maximum allowable amplitude which we can send over these channels? Like, what can be the amplitude of these signals which we are sending?
I mean, that's so this nonlinear effect is giving you a restriction, right? So if we neglect the nonlinear effects, if we just included the linear effects, then we always gain by sending more and more power, right? If we increase the transmitter power, then our received power will increase, our SNR will increase, or equivalently we will increase the link length, right? So the system performance improves. So there is no, if we just include linear effects, then always the more power we have, the better the system performance, right?
Thank you so much.
But now when we include nonlinear effects, we can see that there is a restriction on the power. I can't, if I keep increasing transmitter power, beyond some point actually the nonlinear effects distort my signal so that I actually start losing instead of gaining, right? That's what this is saying.
Thank you, sir.
Right, so if we look at, so here I'm plotting the power per channel, P in, right? So this P total was basically N times power per channel. So this is power per channel in dBm versus the link length that I can get in kilometer. So I'm looking at long lengths here, right, with amplifiers. So I'm starting from 100, and 1000, and 10,000. Okay, so they are really long. And then so here we've got dBm. Right, so you know that a linear, I mean, you know how dBm is defined. So a linear scale in dBm is actually log scale in watts, right? Because this is computed by taking log of the power in watts. So this is also log scale in the absolute power units. So this is 1 milliwatt, 10 milliwatt, 100 milliwatt. So if I want to go to longer lengths, right, from here, I have to reduce the power. So basically, to satisfy this, if I plot this line here, equal to this number, so I get something like this. Okay. So these different curves are for different channel spacings, right? Delta F channel that, of course, will give me a different delta F total. So I've here taken uh, so 8 channels, 8 wavelength channels, and the distance between each amplifier is about 75 kilometers. Okay, so this is 75 kilometers here. Right. So as I increase the link length, I will need more amplifiers. Right. So NA will go up with increasing length. So these are typical. These are typical amplifier spacing for long links.
Sir,
Right.
sir, 8 channels means 8 fibers.
No. There is one fiber. Right. 8 wavelength channels.
Okay. Sir, how one fiber can be divided in 8 channels? Okay, wavelength division multiplication.
Yeah, that's what we are talking about, right?
Okay, sir.
Right. So you can see that as I increase the channel spacing, for the same number of channels, this will go up, right? The total bandwidth. So the power that I can send will also go down, right? So this is for a channel spacing in wavelength of 0.5 nanometer. This is 1 nanometer. This is 4 nanometer. Okay, so you can see that actually yeah. So for the same length, if my channel spacing increases, then I have to send lower power to avoid this Raman scattering induced crosstalk. Okay, so closer space channels are better because I can send more power, which means I can get a higher SNR at the receiver, so lower bit error rate. Okay, so I hope that the plot is clear. Okay, yeah, so the center wavelength here is about 1.55. So we're talking about the C band. So alpha we take 0.2 dB per kilometer. Right, so 100 gigahertz corresponds to about 0.8 nanometer at this wavelength. Okay, so the modern WDM, the dense WDM systems that we use currently are sort of like this one, close to 1 nanometer. So roughly you can see that sort of like if I want to go 100 kilometers, then sort of I can't send in, let's say, a lot more than 10 milliwatts. If I want to go to 1,000 kilometers, then I have to reduce my power to, let's say, 5 milliwatts or something. Okay, so you can see that you need actually better and better receivers because as you're increasing the length, you're also reducing the transmitted power, so the received power also goes down. So okay, so I hope that's clear. Any questions on Raman scattering?
Sir, excuse me, sir.
Yeah.
Sir, unlike in Meridian scattering and Raman scattering, since it's possible to have co-propagation.
Yeah, so we're mainly considering co-propagation only because so we see that the main effect of SRS is basically this crosstalk between different wavelength channels, right? We saw that, for example, if we just had one channel, then the effect is negligible if our powers are much below 500 milliwatts. So typically, yeah, we are operating here in the tens of milliwatts. So, right, so the effect is negligible. But once you have multiple channels, then we see that we have this restriction, right? And all these channels are, of course, propagating from the transmitter to the receiver. They're co-propagating. Right? So that's why we take.
So can I compromise the lower wavelength channels just to compensate the losses, like because the larger wavelengths are.
So this is your right. So this is for the case when we send equal powers in all the regular channels. I can try to do some pre-compensation, right? So I can try to have. So at the transmitter end, I could maybe start with a higher power in lambda 1, right? And then slightly lower in lambda 2 and lambda 3, like that, right? So yeah, so these are the types of things people look at while trying to compensate for the nonlinear. So yeah, that's one thing you could do. You could try to come up with some power profile here that would, yeah, minimize sort of this crosstalk. Yeah. I mean, the problem, it's easy to have equal powers because sort of all of them are traveling through the same, you can then send all of them to the same amplifiers, right, at every stage. If you want to sort of have this different powers, then you have to use like different amplifiers for each channel, right, with different gain settings. So that becomes a little bit more complicated to implement.
Thank you, sir. We already saw that in EDFA the gain actually depends on wavelength. Like it's not.
Yeah. Yes. True. But let's say, I mean, if you're talking about, right, so for example, within the EDFA gain bandwidth, like the entire C band can fit, right? So you can have like, for example, I don't know, 40 channels all within the EDFA gain bandwidth. So maybe like at the edges here, the gain might be different, but mostly for the middle wavelengths, you can get quite flat gain, especially if you operate the EDF in the saturation region. Yeah, but also, I mean, here you need sort of like a monotonic kind of gain spectrum, right? You need higher gain for lower wavelength and then going down. So this kind of thing is difficult to get in a single. Maybe you can do that with. So there are also Raman amplifiers. So again, this Raman effect can also be used for something useful. And one place where they are used in optical communication link is for these amplifiers. So of course, EDFA is the standard amplifier which is used. So it works for the C band and also one can use it for L band. But it doesn't work beyond. So let's say if you want to go to the other bands like S band or U band or whatnot, then you have to use some other types of amplifiers. So there's a very versatile type of amplifier called a Raman amplifier, which basically works on this Raman scattering, right? So we already saw what is happening, right? So you have a pump and a Stokes, and so basically the Stokes gets amplified, right? You transfer power from the pump to the Stokes. So basically you can use this as an amplifier for the Stokes waveform, right? So basically a Raman amplifier is nothing but some length of fiber, and we send in a pump wave, which is shifted from the wavelength that we want to amplify, right? And again, you can play a lot of games with these things. So you can have multiple pumps with each with different powers, right? Each will give its own, right? So this pump will give me some gain profile. I send in another pump slightly shifted with different power, so it will give me another. So I can tailor the total gain profile depending on what pumps I send at what wavelengths and what powers, right? So with this, so one thing to note is that I can build this Raman amplifier at any wavelength I want, because basically all I need is just a pump laser which is shifted, Raman shifted from the wavelength I want to amplify. So it does not depend on some atomic transitions like the EDFA. It depends on the erbium atomic transition, right? So it's restricted to the C band or L band. But Raman basically just depends on the pump wavelength. So as long as I can find pump lasers at where I want, basically I can make these Raman amplifiers at any wavelength. So people have demonstrated Raman amplifiers all across the different bands of the telecom spectrum, and also you can tailor the gain spectrum to whatever you want by changing the. So we'll discuss a little bit more about this later in the course when we discuss optical amplifiers. But yeah, so Raman scattering are used to build optical amplifiers or Raman amplifiers, and there you can try to build different types of gain profiles like that. Yeah, so any other questions on Raman scattering? Okay, so maybe we'll just introduce the next nonlinear effect, and then discuss in more detail in the next class. So these two, Brillouin and Raman scattering, were, as we saw, basically stimulated light scattering effects which were happening due to the coupling of light with the vibrations in the medium, right? So the atomic or molecular vibrations or phonons in the medium, and there was some energy being exchanged, right? So part of the energy of the pump photon was taken away by these vibrations, and then the scattered photon had a slightly lower energy. So they are also known as inelastic scattering mechanisms. So the next nonlinear effect we look at is basically which happens in optical fibers is what is known as a parametric effect, where basically there is no energy exchanged between the light and the medium. Right, the medium just acts as some like a intermediary, and energy is exchanged between different optical fields. So, for example, fields at different frequencies, right? So, for example, these WDM, if you have different wavelength channels, these different wavelengths can exchange energy between themselves, but there is no energy actually given or taken from the medium, unlike the Brillouin and Raman scattering case. Right, so the total energy or the total power in the optical fields, if you add up all the optical fields, that is conserved. Okay, so that is known as a parametric process. And basically, the specific parametric nonlinear process which happens in optical fibers is known as Kerr nonlinearity. Again, named after this person Kerr, who sort of first measured this effect. Okay, so so unlike the light scattering which happens due to the coupling with the phonons or the vibrations, this is actually coming from the electronic. So it's electronic in origin. Basically, it's coming from the coupling of the electromagnetic field to the electrons in the highest orbital of the medium. Right. So in this case, like we'll have some molecular orbital of the SiO bond, where you'll have some valence electrons, right, and they'll interact with the incident electromagnetic field. So you can see that this incident electromagnetic field will apply some force on these electrons, and then these electrons will respond, right? So the optical wave is oscillating at some high frequency, so the electrons will oscillate in response to that. Right. So typically we operate in the linear range, where basically the power of this incident electromagnetic wave is low enough that the electrons also respond at the same frequency, giving rise to linear effects like, for example, refractive index of the medium or absorption coefficient of the medium. Right? But when the incident power goes up or the intensity goes up, basically this orbital starts getting distorted. Okay? So the electrons get pulled out a bit too far, such that basically you can think of like it's like typically you can model these as like mass on a spring kind of thing, right? So it's like a simple harmonic motion. You apply force and then it oscillates at that particular frequency. But what happens is that for very large incident fields, this sort of spring becomes nonlinear. So the force is not just proportional to x anymore, but now you have higher order terms. Okay. Or in other words, the electrons start oscillating at frequencies different from the incident wave. Okay. Another way to look at it is, if you look at like sort of the electron displacement with time, if it looks like a nice sine wave, so I have some incident optical field at frequency omega, and this is, let's say, the electron displacement with time. That is also oscillating at omega, and this displacement is small, right? Basically, the medium is also responding at the same frequency, and you get the linear effects. But if this displacement starts becoming large, what you get is sort of distortions in this electron motion. Okay? So it doesn't look like a sine wave anymore once your displacements become large, sort of order of the Bohr radius or more, right? So then basically this waveform starts now deviating from a sine wave. And now if you take the Fourier transform of this thing, you can see that there will be extra frequency components, not just omega. Right? So that already tells you that the response of the medium will be non-linear, in the sense that it will excite. So again, these oscillating electrons will radiate electromagnetic waves, right? And if they're oscillating, if they have frequencies which are different from my incident wave, then basically I can have some different, like 2 omega or 3 omega, or if I have omega 1 and omega 2, then I could have omega 1 plus omega 2, right? Some different frequencies. Okay, so that's sort of like, without going into too many details, what's sort of happening. So it's electronic in origin, right? So these are very fast, right? Because electrons are very light, they move almost instantaneously to the applied field, right? Whereas we saw for the Brillouin, there was some time scale, right, of this phonon. So that gave me basically this bandwidth, which was very narrow. For Raman, it was slightly wider, but it was still like a few terahertz, some finite bandwidth. These electrons, because they respond almost instantaneously, you can see that basically the frequency response is very broadband. Okay, so it happens over any wavelength almost that you incident in the transparency range of the medium. So for glass, for example, if you are considering again this 1.25 to 1.65 micron wavelength range for optical communications, over this entire band, this current nonlinearity happens. Okay, so there's no bandwidth like the Brillouin or Raman case. It's very broadband because it's electronic in origin. Okay, and basically what is happening here is basically the refractive index of the medium, right? So basically, refractive index is a manifestation of how these electrons are oscillating and then re-radiating, right? So if the electrons oscillate at the same frequency and the radiation is also at the same frequency as the incident light, then the refractive index is just some number which of course depends on frequency, right? We saw in dispersion. But when this displacement becomes large and you go to the nonlinear case, right? This refractive index is, instead of just being a constant, now starts depending on the intensity. Okay, so again, refractive index is basically a result of how these electrons are oscillating, right? And once you go into the nonlinear regime, that depends now on, starts depending on the intensity of the input wave. So basically, the refractive index now starts being dependent on intensity. And then there is some proportionality constant here, which is also denoted by N2 usually. But I just put another subscript NL because in optical fibers we use N2 also for the cladding index. So here N2 comma NL is the nonlinear coefficient. Okay, so this is known as the, so this is your usual linear refractive index that we know, right? So for example, for glass this is 1.45, and then this here is known as the nonlinear index coefficient. Okay, so this you can see has units which are inverse of intensity, right? Because refractive index is unitless. So this N2 is basically meter square per watt, right? So in glass, its value is about 2.6 times 10 to the minus 20 meter square per watt. Okay, so you can see it's a very, very small change, right? So if typically if I look at an optical fiber, right? So let's say if I have 1 milliwatt power propagating in the fiber. So again, we had an A effective here, right? It was somewhere in 50 to 80 micron square. So I can compute the intensity like this, right? And then so the index change due to this Kerr effect if I compute like this, so for 1 milliwatt, this comes out to be about 10 to the minus 12. Okay, so you can see that this change in index here, delta n, is actually very, very small, right? This is 1.45. This is like 10 to the minus 12. So you might think, why are we even considering this? This is totally negligible, right? But again, consider what happens, right? So this mode as it's propagating, it has some wave vector or propagation constant beta, and it acquires a phase, right? Beta z, right? So beta I can write as basically, so the phase acquired here is 2 pi over lambda times n effective times the distance. Right? So now if this index also includes the nonlinear contribution, right? So you can see that I can write this as a linear part plus a nonlinear part, right? And now even if index change is very small, if I'm considering lengths which are really long, kilometers or longer, right? You can imagine that this change in the phase due to the nonlinear part that can easily become like, for example, pi. Right, so you can calculate. So 2 pi by lambda is roughly like 10 to the 6, right? This delta n, let's say, is of this order, right? So you can see for like we can calculate some numbers here, but for kilometer lengths we can get easily changes in phase. Of pi. Okay, so that's how basically again this small effect is building up over long length.